Right now, in this exact moment, billions of devices are communicating with each other across the planet. Your phone, laptop, smart TV, security cameras, cars, satellites, and even refrigerators are constantly sending tiny packets of information through a vast invisible system that connects nearly every digital device on Earth. Every second, photos, messages, videos, bank transactions, and GPS locations travel across this global network. What's remarkable is that this massive worldwide conversation works because of a surprisingly simple idea created decades ago by a small group of engineers who are trying to solve a difficult problem: how to allow billions of machines to share the same internet without causing chaos. To understand how they solved it, we need to go back to a time when the internet was still an experiment. In the early days of computing, machines didn't communicate the way they do today. In fact, they rarely communicated at all. During the 1960s and early 1970s, computers were enormous machines located inside research laboratories and government facilities. If two computers wanted to share information, they usually required a direct connection, one cable linking one machine to another. While this worked for very small systems, it could not scale to larger networks. Researchers began asking a more ambitious question. What if computers in different cities could communicate with each other? What if a scientist in California could instantly send data to a machine in New York? This idea eventually led to one of the earliest internet experiments known as ARPANET. However, engineers quickly discovered a serious problem. As more computers joined the network, communication became unstable. Imagine thousands, then millions, then billions of machines trying to send information simultaneously. Messages could collide, connections could fail, and the entire network could collapse into confusion. If the internet was going to grow, something fundamental needed to change. Instead of building direct connections between every device, engineers needed a smarter system that would allow every machine to share the same network without interfering with others. The solution they created was surprisingly elegant. Instead of sending information as a single large message, break it into tiny pieces. These pieces are known as packets. Think of it like mailing a book. Instead of sending the entire book in one box, you tear it into individual pages, place each page in its own envelope, and send them through different postal routes. Some envelopes might travel by truck, others by plane, and some might arrive earlier than others. When they reach their destination, they are reassembled back into the original book. This concept is called packet switching, and it completely transformed digital communication. Every time you send a message, watch a video, or open a website, your data is divided into thousands of packets. Each packet carries a small piece of information along with something even more important, an address telling the network exactly where that packet needs to go. This addressing system is powered by the Internet Protocol, commonly known as IP. Every device connected to the internet receives an IP address, which functions like a digital home address. Your phone has one, your laptop has one, and even your smart doorbell has one. When packets travel across the internet, they use these addresses to find their destination. Specialized machines called routers read the addresses and determine where each packet should go next, guiding traffic across an enormous global system that operates much like a massive transportation network with millions of intersections and billions of moving data packets. What many people never realize is that the internet is not floating invisibly in the air. Behind every message, video call, and search request lies a vast physical infrastructure spanning the entire planet. Beneath the oceans, massive fiber optic cables stretch for thousands of kilometers. These cables, often only as thick as a garden hose, carry the majority of the world's internet traffic. Inside them, information travels as pulses of light moving through glass fibers at incredible speeds. Across continents, enormous data centers quietly manage global internet activity. These facilities, often as large as football stadiums, contain hundreds of thousands of servers connected by miles of cables and supported by powerful cooling systems. When you watch an online video or load a web page, your request may travel through multiple routers, cross cities, pass through undersea cables, reach a distant data center, and return with the information you requested, all within a fraction of a second. One of the most impressive features of the internet is its ability to adapt. If one route becomes congested, packets automatically take a different path. If a cable breaks or a server fails, traffic reroutes through alternative connections. This resilience was part of the original design philosophy: create a network that could continue functioning even if parts of it were damaged. Today, this system connects more than 5 billion people and even more devices. In fact, the number of connected devices has already surpassed the global human population. Smart homes, wearable devices, industrial machines, autonomous vehicles, and countless sensors embedded in cities, farms, and factories constantly exchange packets through the same global network. Streaming a movie sends thousands of packets racing toward your device. Sending a voice message converts your voice into packets that travel across continents in milliseconds. Modern life depends heavily on this system working smoothly. Financial markets, hospitals, air traffic control, emergency services, and global commerce all rely on constant connectivity. Without packet-based networking and IP addressing, the digital world we depend on simply could not exist. However, the internet was never originally designed for billions of devices. When IP addressing was first introduced using IPv4, engineers believed it could support about 4 billion unique addresses. At the time, that number seemed unimaginably large. But as the internet expanded with smartphones, smart homes, and the Internet of Things, those addresses began running out. To solve this problem, engineers developed IPv6. While IPv4 allowed roughly 4 billion addresses, IPv6 expanded the address space dramatically to about 340 undecillion possible addresses, a number so large it contains 36 zeros. This enormous capacity ensures that the internet can continue expanding for generations, supporting trillions of devices across the globe. And expansion is exactly what is happening today. New technologies are pushing the boundaries of connectivity. Satellite internet systems such as SpaceX's Starlink are launching thousands of satellites into low Earth orbit, delivering internet access to remote villages, ships at sea, and aircraft flying across continents. Meanwhile, faster wireless technologies like 5G are dramatically increasing the speed and capacity of wireless communication, allowing cities to become highly connected digital ecosystems where infrastructure, vehicles, and devices communicate continuously. Yet this growth also introduces new challenges. Security risks increase as billions of devices connect to the internet, and each connected object becomes a potential target for cyber attacks. Data privacy becomes more complex. And managing network congestion becomes increasingly difficult as artificial intelligence and modern technologies generate enormous amounts of data. Because of these challenges, engineers are constantly improving the network. Researchers are exploring smarter routing systems, ultra-fast optical communication technologies, quantum networking experiments, and entirely new architectures for the future internet. The truth is that the internet is not a finished invention. It is a constantly evolving system, a living network that grows alongside humanity. And despite its incredible complexity, its core principle remains beautifully simple. Break information into packets, give every device an address, and allow the network to determine the best path for delivery. That one elegant idea allows billions of devices to share the same digital highway. Every message, video, website, and piece of knowledge travels across the same invisible system at the speed of light, crossing oceans and continents in milliseconds. The next time you send a message or load a web page, remember that your data is not traveling in a straight line. It is being divided into pieces, racing through cables, routers, satellites, and servers around the world, often taking dozens of different paths before quietly reassembling itself on someone else's screen. It is a silent global choreography, billions of devices and trillions of packets moving together in precise coordination, powering the connected world.